Now that we've discussed paths and circuits, we're going to talk about some special types of paths. We're going to talk about Euler paths and Euler circuits. I know the name looks like it's pronounced Euler, but it's a Swiss mathematician, and the pronunciation is actually Euler. Euler paths and Euler circuits have some applications we can talk about in a little bit, but the basic idea is that you're going to make either a simple path or a simple circuit using every edge. And there are sometimes some doodles that people draw like this, where you can draw a picture without actually retracing your steps at all, and this is something that would represent an Euler path or circuit, but there are more important applications than just simple little doodles. And there's a sort of famous problem called a Königsberg Bridge, where you had a bunch of land masses and a bunch of bridges, and the question was, could you take a walk around crossing every bridge exactly once? But there are some more important applications. Okay, so let's talk about finding an Euler path or an Euler circuit. An Euler path, right, would be a simple path. That means that you don't retrace any edges or reuse any edges. It uses every edge. Okay, so if you wanted to make a path, right, the question really is, where would you start? You could start pretty much anywhere to try, and you could sort of see what it would mean. So we're trying to move around, and when we get to D, we have a little bit of a problem, right? If we decide to go this way, right, then we're never going to get back to this edge over here, right? However, if we try to go this way, right, then we're going to have to retrace our steps. So we'd have to sort of try again. So what if we started somewhere like here at D? Right, so we can go this way, we can go this way, we can go this way, but we're going to have a similar dilemma. If we go this way, we lose A to B. If we go this way, we're stuck at A. Okay. And hopefully you would see, with a little bit of trial and error, that it's really not going to matter where we start. We're going to have a problem getting an Euler path for this particular graph. So right now we're just going to say that it doesn't look like there's an Euler path. Okay. And if there's not an Euler path, you're not going to be able to find an Euler circuit, because if you can't even get to starting into two different points, there's no way you're going to be able to make it back to yourself. Okay, now it turns out that we'll have actually very definitive tests for Euler paths and circuits, which is something that we haven't really seen much in this graph theory chapter. And we're going to sort of observe what's happening in these two graphs down here. So looking at this graph G over here, let's just sort of reflect a little bit about what happened over here. Right? The idea is you don't want to get stuck. Right? So if you decided to go this way, you would get stuck at the vertex B. And if we look a little bit more closely at the vertex B, it has a degree of 3. Right? You have 1, 2, 3 edges associated or incident with B. Right? And if they come in pairs, right, every way in would provide a way out if they came in pairs. But you had this last edge here that didn't provide, it provided a way in but not a way out. And we're going to be able to basically use that strategy to help us find Euler circuits. So we're going to start actually with an Euler circuit down for graph G. And in this case, it turns out we could start really anywhere we want to. So we could start at C. Right? And ultimately, we would have to write the actual circuit down, and we could use little arrows to show the path. So first, let's just kind of draw it to make sure we can do it. All right, we could go this way, this way, this way, this way, right? And we have there an Euler circuit. So we started here, we went this way, we went this way, we went this way. Okay. Now, if you just sort of looked at this after the fact, you might have to actually number these at 1, 2, 3, 4, 5, 6, 7, or you could write the path down. I went from C to F to B to E to D to A to B and then to C. Okay, so to be complete, you might want to show this is the easiest way to represent it. Visually speaking, you can do something like this. As a graph gets larger and larger, it gets harder to kind of read all of your little notations on the graph, and it gets harder to follow all of the arrows. But one of the reasons it made sense to even attempt an Euler circuit here is every way into a vertex had a way out, right? And let's look at the degrees of these vertices, right? Vertex C has a degree 2. Vertex F has a degree 2, vertex E has a degree 2, degree 2, degree 2, and B has a degree of 4. right? That means for every way in, there's a way out. For every way in, there's a way out. That guarantees that you'll never get stuck, right? So if all of your vertices have even degree, you should be able to make an Euler circuit. Okay, if you look back up at the example up here, look at F has a degree of 3, D has a degree of 3, B has a degree of 3, A has a degree of 1. We have a bunch of vertices with odd degrees. We won't be able to find an Euler circuit there. Okay, but let's look at this graph H over here, and let's observe the degrees here, 2, 3, 3, 2, and 2. Okay, we don't have all even degrees, so you could get stuck at B and you could get stuck at C. Right? That means that one of the times you'll be able to come in without going out, or you'll go out without being able to come back in. Okay, but for an Euler path, right, you don't need to end up back where you started. So as long as you have only two vertices that are odd, right, in degree, you can make one of them the starting point and one of them the ending point, because the first time you step out of B, you may never need to get back there. And if you do, there's always the rest of these degrees correspond to pairs of edges. Right, so if you take the first step out, now you're down to an even degree. Every way you come in, there's an equivalent way out. And the same thing over here. So what we could do here is we could start at B, and then this becomes sort of arbitrary. So I wanted to do this in blue. Okay, we go down here, then we go up here. Okay, now we came in and out of C. There's still one more edge with C, but that's going to be the last one that we come into, right? So we left B without having to come back into it, and if we did, we came in and out. And then when we went in and out of C, the last time we hit C, we never had to come back out. So if we start here, right, our path went like this, it went like this, it went like this. Okay, if we wanted to number these, we'd say 1, 2, 3, 4, 5, 6, and we could again write that Euler, this actually here just to label it clearly, this is our Euler circuit. And then over here, my C's don't look very good there, this would be, we'd start at B and go to D, and then we went to C, and then E, and then A, and then B, and then C. So we started at B and we ended at C, and we used all 6 edges. This is an Euler path. Okay, so our observations here are that if every vertex has an even degree, you'll never get stuck, because for every way in, there'll be an equivalent way out. For an Euler path, but no circuit, you're allowed to have 2 vertices with odd degree. Those will be the starting and ending points. And these are not unique. There's no reason that you had to start by going from B to D. You could have gone from B to A. You could have started at C and ended at B. But whichever 2 vertices have your odd degrees, those are the ones you're going to begin and end at. Okay? So the theorems here are stated a little bit more clearly. Right, a connected graph with at least 2 vertices has an Euler circuit if and only if every vertex has an even degree. A connected graph with at least 2 vertices has an Euler path, but not an Euler circuit, if and only if there are exactly 2 vertices with odd degree. Those 2 vertices must be the beginning and end of the Euler path. Okay? Now, once the graphs get large, it becomes a little bit more tedious to find the Euler circuit, but the general strategy is you could sort of find a circuit and remove it, find another circuit and remove it, and then just figure out a way to kind of insert one circuit into the other. So if you had a circuit here that went from A to B to E to D to A, and then you had another circuit here that went from B to C to F to B, you could then take this second circuit BCFB, and when A goes to B, just kind of drop it right in there. So you could have gone from A to B and then followed this circuit and then hop right back onto the original circuit. So as graphs get larger, the idea is you find small circuits, remove them, find small circuits, remove them, and then just sort of insert them in. Okay? So practice, there is a nice clear definitive test. You should be able to tell for any graph definitively whether it is an Euler path with no circuit or an Euler circuit.